Term test 2 will be held on November 3rd, today, 6:30 to 9. 3 questions, PGCLL 127. And another thing, Thursday, there will be lecture, okay? So I know some of you have a term test coming on this coming Thursday. I will record this lecture. Are we clear? Okay, so today's lecture, I also record. Some of you will not be here because of the term test. Right, so we are going to go into acceleration. It's not any more difficult. It's just a bit more tedious. Okay, just a bit more tedious. So if we have 2 points on a rigid body, as what the image shows down here. Okay, so we will have this image available on Avenue to Learn. So you have 2 points, and 2 points are on a rigid body. And both points are under, or the rigid body is under general motion. Okay. So to write this out, the acceleration at point B will be equal to the acceleration at point A plus, now you have 2 extra terms coming in, is acceleration of point B relative to point A in the tangential format or in the tangential direction, and you have A acceleration of point B relative to point A. Now you have an N. Okay, so I will define what they are. Okay, so we know that A subscript B is acceleration. Of point B, and then A subscript A, capital A, is acceleration of point A. And then the next one, we have A acceleration of point B relative to point A in tangential, and this is the tangential acceleration of point B with respect to point A. Okay, and then if I were to write out the formula, A, B, and in the tangential direction, this will be equal to alpha cross R, B from point A, where alpha over here define the angular acceleration. And then we have another term, which is A, B, and now it's normal. So what we have over here is the normal acceleration of point B with respect to point A. Okay, and to calculate this, you have A, B relative to N, and then the normal direction. Now this will be equal to omega squared. Okay, and then we have R, B, A. Okay, so there is no crossover here. Okay, so it's a direct multiplication that we can see later on. Okay, so from, as I said, you have more terms to consider. Okay, so from equation number 1. I think I did call that equation number 1. Yep. From equation number 1, what we have is a B, okay, of point B is equal to acceleration at point A, and then plus by alpha cross RB from point A, and then we have to insert minus omega squared, okay, RB from point A, okay, and I like to highlight this is due to tangential acceleration, and this is due to normal acceleration. So this term over here is point B relative to point A. Okay. So I'm going to have a diagram for you. Okay. If you all can leave this diagram up. So I want you all to focus on this term over here. Okay. So we have A, B, acceleration of point B relative to point A in the normal direction. Now this will be equal to minus omega squared RB from point A. Why negative? Because it's pointing towards, I'll use a different color. It's pointing towards, okay, the center of rotation. Okay, so that's why we have it as negative. Now, a common thing to write down, if the acceleration, right, when acceleration in the normal direction, okay, is equal to omega squared r, and this omega squared r you have seen before. Okay, so this is again relative to the center of rotation, and I always want to highlight to you that this is relative to the center of rotation. Okay, so note we are also aware that velocity is equal to r omega, and omega is equal to v over r, right? So therefore the acceleration in the normal direction can be written as v squared over r squared multiplied by r, and this is equal to v squared over r. Okay, again I like to highlight this is really important. Okay, we have to be careful over here. Okay, so the next thing we are going to look at a problem. Okay, so from this problem you can learn quite a few things. Enough of the theory. Okay, so this is our example number 1. So we are given, at a given instant, the top end means at this configuration. Again, you will see the word at the given instant, at this moment. Okay. At the top end A of the bar has a velocity and acceleration shown. Okay, so we have VA equals to 5 feet per second. We have AA at 6 feet per second square. Okay. Determine the acceleration of the bottom B and the angular acceleration at the instant. So what we have to find, they want us to find the acceleration at point B. Okay. And then they also want us to find the alpha of AB. Okay. So I assume alpha to be going in a clockwise manner. Okay. In a maybe I assume wrongly. Okay. Let's look at assumption. So we just sketch. Okay. So we just sketch. So this is at this instant it will be, right? So this is our point A. And this is our point B, right? And then when point B moves, so this is at 60 degrees. Okay. And then when it moves, okay, so I rotate over here. So now this is B prime, and this is A prime. Okay. So now, for example, I call this less theta is less than 60 degrees. So it seems that alpha AB should be rotating in that direction over there. Okay. So when that's the case, I'm going to I'm going to assume, okay, I'm going to assume, right? This is the direction. Yeah, I'm just going to assume for now. Okay. Okay. So from here, the formula that we are going to use is we're going to find AB is equal to acceleration at point A plus by alpha cross R B from A, okay, and then plus by omega squared R B from point A. So if we look at over here, what are the unknowns? So the unknowns are A at point B, we don't know. We also don't know what is our alpha, and then we also don't know what is our omega. Okay. So given we have velocity at point A, and this is equal to minus 5 feet per second. Okay, so when I put minus, it's because it's coming down in a Cartesian format. And we know that acceleration at point A is going at minus 7 j feet per second squared. Okay.